You hear about AI all the time, you hear about quantum computing. They're both seen as these huge, separate revolutions. But what happens when you smash them together? That's what we're digging into today, the powerful fusion that could unlock a completely new frontier of problem solving. So let's start with a big question. AI is doing some incredible things, right? But it has its limits. There's a wall. What happens when our very best algorithms running on our most powerful supercomputers just get stuck? What happens when they run into problems that are just too massive, too complex for them to handle? And that barrier, that's what we're calling the computational wall. To really get why quantum computing is such a game changer, we first need to understand the fundamental limits that today's AI is already crashing into. For decades, the name of the game was simple: make transistors smaller to make computers faster. But we're hitting a very real, very hard physical wall. We are now building computer chips at the scale of atoms. And you can't really get much smaller than an atom before things get, well, weird, and quantum effects start messing things up. So this physical limit creates some huge roadblocks for AI. For instance, in logistics, trying to find the most efficient route for a global shipping network creates what's called a combinatorial explosion of possibilities. We're talking literally more options than there are atoms in the known universe, no joke. Or in medicine, trying to perfectly simulate how a new drug might interact with a protein is just too much for today's computers. They have to approximate, and that's just not always good enough. So if we can't just keep building faster classical computers forever, we need a totally different way of thinking. And that brings us to quantum computing. It doesn't just play the game better, it plays by a whole new set of rules. Okay, so we all know the classical bit, right? The device you're watching this on right now is built on this super simple foundation, a switch that is either on or off, a 0 or a 1. It's reliable, it works, but it's also limited. Now meet the qubit. And this is where things get a little weird and a lot more powerful. Because of a quantum property called superposition, a qubit can be a 0, a 1, or both at the exact same time. You can think of it like a spinning coin. While it's still in the air before it lands, it's kind of both heads and tails at once. That ability is its superpower. This chart really just lays it all out. A classical bit is certain. It's a 0 or a 1. A qubit is all about possibility. It's a 0 and a 1. Now, this leads to a mind-blowing difference in power. With classical computers, you add more transistors, you get more power. It's linear. But with quantum computers, adding just one more qubit can literally double the computer's processing power. That's exponential growth. And it gets even crazier with another property called entanglement, where qubits can be linked in this mysterious way, sharing information instantly no matter how far apart they are. All right, so we've got an AI that's hitting a wall, and we've got this new kind of computing with mind-bending power. You know what comes next? Let's bring them together. Let's look at exactly how quantum's strange new rules can smash through AI's biggest roadblocks. It really boils down to three main areas where quantum gives AI a massive power up. One, it supercharges optimization for those problems with bazillions of possibilities. Two, it unlocks truly realistic simulations of the real world. And three, it can actually enhance machine learning itself to create way more powerful models. And this isn't just about going faster. It's about doing things that were literally impossible before. Let's start with optimization. Remember that logistics problem with all the shipping routes? A classical computer has to trudge through every single path, one by one. It's slow. A quantum computer, because of superposition, can essentially explore a vast landscape of possibilities all at once, homing in on the single best solution exponentially faster. Next up, simulation. And this one is a huge deal. This is the difference between a rough guess and, well, reality. When we're trying to design new medicines or new battery materials, classical computers have to take shortcuts. A quantum computer doesn't. Because it's built on quantum principles, it can simulate molecules with perfect real-world accuracy. It models every little interaction exactly as it happens in nature. Okay, so this all sounds great in theory, right? But this isn't science fiction anymore. Companies are already pairing quantum and AI to solve real, tangible problems. Let's look at a few examples of this in action right now. Let's take Volkswagen. They looked at the insane traffic gridlock in Beijing, a massive optimization challenge. Using a quantum algorithm, they didn't just find the best route for one taxi. They calculated the optimal route for all taxis at the same time, figuring out how each car's decision would affect every other car. The result? less congestion, shorter commutes for everyone. Then you've got healthcare. Biotech giant Biogen used quantum-enabled AI to crack a huge bottleneck in discovering new drugs, comparing massive complex molecules. Their new method speeds this up dramatically, which could potentially shave years off the search for new medicines. And of course, there's finance. JP Morgan Chase is using quantum AI to get a serious edge. They're tackling huge problems like optimizing trading strategies and assessing risk by simulating market scenarios more efficiently than ever before. The key thing here is that this isn't coming soon. It's happening right now. But we've got to be real here. As powerful as this tech is, it's still super early. It's not a magic bullet yet. So let's take an honest look at the challenges that still need to be solved. Right now, the big hurdles are pretty fundamental. First, today's quantum hardware is noisy. The qubits are, well, they're divas. They're incredibly fragile, and the slightest disturbance can cause errors. Second, there's this weird problem called barren plateaus, where a complex quantum AI model can essentially just give up. It just stops learning. And finally, there's the huge challenge of just getting our massive classical datasets loaded into a quantum state in the first place. But here's the good news. Some of the smartest people on the planet are working on these problems. One really promising idea is called data re-uploading. Think of it like this. Instead of just dumping all the data in at the beginning, this method lets you inject bits of classical information multiple times throughout the quantum calculation. It can make the whole model a lot more powerful. You can even chain these re-uploading layers together to build more and more complex models. But, and this is a big but, it's a super delicate balancing act. Researchers have found that adding too many layers can actually make the model harder to train, running you right back into that barren plateau problem. It's a perfect example of the complex puzzle that researchers are trying to solve right now. But even with those challenges, you can just feel the excitement in the air. This quote really sums it up. The fusion of quantum and AI isn't just a small step forward, it really feels like the dawn of a transformative new era. So when we look to the horizon, what are we talking about? This isn't just about faster computers. We're talking about tackling some of humanity's grand challenges. Things like personalized medicine designed for your specific DNA, climate models so accurate they can guide global policy, supply chains that are so perfectly optimized they have zero waste, and even developing brand new forms of unbreakable encryption. And that really brings us to the final and maybe the most important question. We're on the verge of creating a tool with the power to solve problems we once thought were literally unsolvable. So the question is no longer just, can we solve them? But with this incredible new power, what should we solve first?